All right, we're in Windows world again, and this time we're in deep Windows world. Please introduce yourself. You guys work on the lowest level of the system, the PreOS environment. Who are you?
That's right. I'm Andrew Ritz. I'm a dev manager for a group called the Platform Architecture team.
Excellent.
And I'm Jamie Schwartz. I'm a dev lead for Andrew.
Okay, cool. So let's talk a little bit about this. What is the PreOS space? What do we mean by that?
Yeah, so the general idea is that when you flip the machine on, it's not automatically running an operating system.
Yeah.
So it starts off and runs all this firmware code, and we're the guys that basically bridge the gap between the firmware code running and the Windows kernel getting up and running and executing on the processor. So it's a kind of wild and woolly world that's full of like all these crazy standards and specs and things like that we have to navigate. It's a really exciting environment.
I bet.
Yeah.
And you guys, of course, you've innovated in this space in Vista with the notion of EFI. And can you talk a little bit about like what you've done specifically in Vista? And we should probably also step back and talk about exactly what happens. Like,
yeah,
how
sure.
do you communicate with this firmware? What kind of messages? What are these things?
Yeah. So, like, just to give a little bit of a historical perspective. I guess the typical PCs that people use today are based on this firmware called BIOS that I'm sure you're all familiar with.
Yeah.
It harkens back to the PCAT. It's like a 25-year-old, 30-year-old technology.
Wow.
It's pretty old, and really the underlying architecture for BIOS firmware hasn't evolved much in that time frame. And you can just imagine all the sort of technology innovations that have happened in that time frame. And so it's starting to show its age, as you might imagine. Back then, people used to program all the time in 16 bits in real mode. And well, it's still a real mode environment today, so that alone makes it like a really challenging place to innovate in. But people have like a lot of interest in doing cool stuff in the boot environment, in this pre-boot space. We have to support boot off of USB or off of iSCSI or any number of like crazy different devices people have come up with that people weren't dreaming about in 1985 or 1983 or whenever this thing got kicked off. There's a lot of interest in security, things like that as well. So anyway, it basically, our code base, if you can imagine it, like started off, in NT and hasn't changed much in this boot environment. It was starting to show the same age. Just that part of it has to run in 16-bit mode is crazy because we don't even have the 16-bit compilers really generally available anymore. We have to have our binaries, some special binaries checked into our tree because the compilers aren't there anymore. And people that know how to program in real mode are in short supply. It's not like they teach that stuff in school at all.
I mean, there's no realmode.net yet?
No.
So what language what do you write your code in? I mean, what do you spend your time writing? Assembler? What?
Well, everything from 16-bit real mode code to 64-bit long mode. So one of the things that we really tried to do with the rewrite of the boot environment is to write as much of the code in C in either 32-bit or 64-bit mode. So if you break up the boot process, you have some amount of 16-bit real mode code that will bootstrap you up into a 32-bit protected mode. And so when you think about our boot flow, which we should probably draw up on the board in a few minutes, is the main piece that most people will think of is the Windows boot manager. And that on a typical PC with a BIOS is going to be 32-bit protected mode. When you transition into the actual bootloader, we've implemented the bootloader in the operating environment of the OS and in the kernel. So for a 64-bit platform, that's going to be 64-bit, and that's a deviation from what was done in the past. And it really does make the development much easier because you're doing a lot less thunking and you're getting to write in the operating mode and that you're familiar with and using the tool set that you're familiar with.
Excellent. So let's do that. Let's talk about what happens when you boot Windows Vista.
Sure. So I'm going to go with a sort of BIOS presentation here of how the system works. What's kind of interesting is that Windows NT kernel is based off of this ARC architecture, ARC architecture that was used on digital alpha platforms. And there's not really any of those in existence anymore. So it was interesting that in the past, what would happen was that everything would sort of thunk from BIOS into ARC, and the kernel speaks in ARC.
Okay.
So, and so we sort of re-implemented this thing to be firmware independent kind of flow. Let's see, how can I do this? I'm left-handed, so I've got this challenge writing on a whiteboard that everything erases unless I write really sloppy, so I'll apologize for that.
Not a problem. I can read it. So here's like a really simplified diagram of how a system works. Okay.
But what happens is that when we decide to boot up the system, the BIOS will decide, like a lot of people have seen these BIOS screens that say, do you want to boot off of a CD-ROM or a disk or what
Absolutely.
have you. Let's assume that you're deciding to boot off of a disk.
Okay.
What that means is it's going to transfer to a piece of code that Microsoft supplies that lives in this thing called the master boot record. So there's like a really limited, only a couple hundred bytes of code that can live there. And really all that thing does is, and this is 16-bit code, that basically transfers over to some file system specific boot code. So like if you're running an NTFS partition, which we prefer in Vista, that's the only one we support, it'll run this NTFS specific boot code. And that boot code really just has the smarts to find this file called bootmugger that sits in the root directory of the hard disk.
Okay.
So bootmugger will get launched, and this is the thing that presents a menu that many of you are familiar with. It says you want to boot Windows or prior version of Windows or what have you.
Okay.
The bootmugger runs on these systems in sort of 32-bit mode. So it's like a 32-bit binary for the most part,
okay.
and runs in 32-bit protected mode. The boot manager, or bootmugger, ends up loading this program called winload.exe. So one of the nice things we did in Vista with this re-architecture is we made it such that like winload.exe and the kernel are on the same partition. So they're matched with each other. So this is like a really great simplification over prior releases where we had this file called ntldr or ntloader. And the ntloader had to work with all the prior versions of operating systems if you were doing a dual boot or a multi-boot. So that means like the Vista ntloader would have had to support XPSB2 and
Windows 2000,
Windows 2000, NT4, and back quite a way. So it made it really hard for us to kind of make and put changes in. So,
that's a big architectural change.
A big architectural change there. Yeah.
Cool.
So this guy winload.exe, what it generally does is it sets up the execution environment for the kernel. And as Jamie was mentioning before, it runs in the same operating environment as the kernel. So it'll run in 64-bit mode if you're running the x64. Booting the x64 version of Windows. This thing really just loads all the boot start drivers off of the disk and into memory, loads the kernel into memory, and it does all kinds of crazy stuff like sets up all the binding and import tables and all those things correctly. And its real main job is like any other sort of C program. The kernel has got sort of a main, like any sort of program does. But the arguments to main in the kernel are this thing called the loader parameter block. So it establishes all these things that says like, what are all the boot start drivers, what's all of the RAM in the memory, what's the physical RAM in the system that's usable to put operating system code in and data, things like that. So it sets up all this big environment and passes it into the kernel. And then the kernel will go ahead and sort of start initializing itself.
Excellent.
Yeah.
So that's you. That's you guys.
That's right. Yeah.
Excellent.
So we do a lot of interfacing with this boot code, in firmware code in order to get the files to load off of disk, and or to ask the firmware to tell us what RAM is installed on the system, how much, where's it at, what are the physical page numbers, and sort of those kind of attributes.
Absolutely.
So you might want to mention now, on an EFI system, the flow is identical except for there's no master boot record and there's no file system boot code. So the first part of our code that is actually executed is the Windows boot manager itself. And that gets loaded from this thing called the EFI boot manager, which is just a boot manager that's part of the core firmware itself.
Okay. Now let's talk a little bit about EFI. I mean, what's the benefit besides running less code at the very beginning? I mean, if you're saying it removes two of the necessary constructs, what else? I'm being simple.
I'll sit back down again. So as Andrew was saying previously, BIOS is all 16-bit real mode code. And it's a hard time finding any developers that can program it in 16-bit real mode. It's also very difficult to innovate. So EFI is this firmware interface that is defined to be 32 or 64-bit depending on the width of the processor, and it's very calm or object-oriented in feeling, and so you basically have this interface that can be written in C or C++, and so you can get the developers that actually know how to program in this environment. You have the tool set that actually exists to compile the code, and all of a sudden you've created the ability to innovate in this space.
So it's probably worth mentioning that EFI stands for Extensible Firmware Interface. So extensibility was sort of baked into this thing from the start. And so they've got these things like sort of like C++ objects or classes that can be used to manipulate things. So there's like a great abstraction for dealing with block I/O on a system, which is pretty cool. We started working on EFI to support Itanium boot back in the late 90s. So it's something I've been working on for pushing a decade now. And I guess probably around 2001, we decided that this EFI thing was pretty good on Itanium and really got pretty serious about starting this boot architecture project with the aim that we're going to take this EFI that's a lot cleaner architecture and interface and try to make a concerted effort to really transition the x86 systems over to EFI. So so it was probably 2001 that we started writing code. Or doing the design.
We started the project, we started thinking about this, and then I think the very first line of code was written in October 2002.
Nice.
But we had the design and kind of the layout pretty much in mind at that point.
So let me ask you guys a question. When you talk about, I'm just trying to wrap my head around the notion of innovating in the PreOS space.
Yeah.
What's an example of how we could, some other third party or whoever, some dev out there could innovate on EFI? Like, what are some of the things that I could do? Besides,
so one of the main pieces of innovation are really for guys that are building systems. So the main piece of innovation is that it really quickens the release to manufacturing cycle for somebody that's doing a bring up, because they don't need to get their core firmware and such running in 16-bit mode so much. It's much more rapid, environment. We're using modern tools, and it's not such specialized knowledge. So that's where some of the main innovation is enabled. For us, there's a lot of innovation we wanted to do in terms of supporting all these different kinds of boot types. Supporting really rich and nice-looking graphical experience for boot up is something that we were interested in doing. So that was a neat innovation place or point. Another main innovation area was with BitLocker and security. So the BitLocker feature was something that we were able to leverage this new trusted platform module hardware and use the TCG interface spec and such to provide this more secure boot experience and do volume level encryption integrated into the OS, which is a really exciting thing to have helped put together. What other pieces of areas of innovation are there? I mean, for us, we've got this whole boot environment that we put together, and it's the boot environment allows us to build all kinds of apps. So we built this memory diagnostic, for example, that runs in this environment. We've got a whole set of sort of acceptance tests and such that run in this environment. The memory diagnostic is a nice one because it integrates well with the OS loader, allows us to like detect RAM that's going bad. We can mark it offline and no good, stop using it, which is a
and continue the boot.
And continue the boot. So
Nice.
just kind of like you have disk sectors that are going bad and you stop using them, you can have the same concept now with RAM. Sort of just integrated by default into the OS.
And I know that I've been doing some talking with the diagnostics people who are just glowing about the work that has gone on in this space, in the sense that Windows Vista will theoretically only not boot once. Theoretically.
Theoretically.
I mean, assuming you have, assuming that software is the problem and you just don't have, your hard disk is dead or you don't have your RAM broken or whatever's going on. But theoretically, because of some of the work that you guys have done, you'll know to be able to restore the system if there's a restore point. Can we talk about that a little bit? I mean, that's an example of...
The main work that we did for the Windows recovery team had to do with logging information, similar to a lot of the other work that they did. It really required a large amount of tracing such that they could look through that information to try to diagnose what went wrong. So we did some amount of work to help trace certain things that happened during the bootstrap process and certain failures during the bootstrap process, such that their code can then take this information and diagnose what really went wrong during boot.
Another nice thing we put in was this idea of having boot sequences in the system, so we can have I guess a list of things that's supposed to happen. So we're supposed to like launch the boot manager, and if things go well, it's supposed to launch the win load that we had up on the board.
Yep.
If the win load fails, it's going to return back to the boot manager, and because we have these boot sequences, we can say if you run that thing and it returns back to the boot manager, run the next thing in the boot sequence, which is the Windows recovery environment. So it allows us to take any of the logging of what went wrong during Windows the win load process and pass it on to this WinRE so that it can go ahead and be able to do the seamless experience. We use that same idea when we're running the memory diagnostic. So the memory diagnostic will say which pages are gone bad, and that can be presented in the Windows recovery environment or in the OS.
Absolutely, and the thing is that now these types of, like, it's not the case on earlier versions of Windows, right? Diagnostics in Windows, if XP doesn't boot, it's not going to boot. It's just not going to boot. You have to install a new operating system, or you have to call your uncle who works at Microsoft and have him not figure it out for you.
Yeah. Another cool thing we put in for them was support for RAM disk boot. So that was always a major sticking point for us during the install of prior operating systems. We always had to press F6 to get their mass storage driver to get loaded or what have you, and we got rid of that completely from Windows Vista. We just don't need it anymore because we load everything into a RAM disk and then boot out of that RAM disk. So it's not required that your mass storage driver, like your SATA disk driver or controller driver, is up and running for the Windows OS boot process to progress, because we're running everything out of RAM. So then once you get into setup and you're running sort of the high fidelity setup experience, you just use that to get the storage driver up and running. And this is like a really simple thing here, is that we used to require a floppy drive for F6, to put in these drivers. And it's like a little complicated to get drivers off of a CD-ROM. But because we have this F6, we don't have this F6 support anymore. We got this RAM disk based thing. People can just ship their drivers on a CD-ROM. So bye floppy drives. We don't need them anymore. So it simplifies, pretty fundamentally the experience of like bootstrapping the install of the OS.
Awesome.
Yeah. And something like that would have been really difficult to do in the old code base. Like, we had done stuff like that for embedded and things, but the old NT loader was originally written with a 16 megabyte address space. So can you imagine trying to fit a Windows image into that? There were some iterations done over time to allow that 16 meg address space to grow, but it couldn't grow in a dynamic fashion. And so when we went back and to square one and really thought about, what does it mean to be a PreOS application? What's the functionality that's required? We really thought about things like having a dynamically growing address space and things like that, such that things like this RAM disk boot would be possible, and regardless of the size of OS image.
Very cool. So, I've noticed this, and, we don't really ever talk about how it's possible. I'm not sure. I mean, you have to be involved to some degree, but Vista boots fast. I mean, if you guys done work in that area to speed up boot?
So Jamie is the master of caching strategies, right? He's got,
Nice job, man.
we've got some amount of caching that goes in there, but there's a set of technology to try to lay things out on disk so that our cache will be effective. So we profile over boot what happens so that this block cache that we have in place will be effective. So
most of the work in this area is done by the performance team, and because even if you look at boot, while there's a lot that is required to get into the kernel, there's a whole lot more that happens after you're in the kernel. So there's even more disk I/O there, and so most of the work that they do is in that space and not in our space. So, we have some tracing in there, and they do look at those logs, and they try to optimize, block layout based on that and all that stuff. But it's really all the performance team, and most of what they're looking at is actually after our code.
Cool. And now you already mentioned things about adding some more security to the pre-boot space.
Yeah.
But most people don't really think about the danger, any kind of potential exploits in the PreOS space, right?
Yeah.
Like, I could imagine someone could rewrite maybe the boot manager or have the system load DLLs that aren't signed. I mean, I don't know what the exploits would be, but you guys have blocked the possibility of that happening, or
let's talk
about it.
We did a lot of work with this idea of supporting code integrity in Windows Vista. So code integrity is a policy that we have on by default for our 64-bit operating system. So it requires that all binaries are basically digitally signed. So it's a really nice enhancement. So it means that you can't tamper with one of these things and have it have the system boot. It'll detect that and reject the driver and say that it's not signed and halt. So that alone is a really nice enhancement. And I already mentioned BitLocker earlier.
Yep.
BitLocker allows us to sort of measure the signature of the boot manager. So if somebody were to tamper with the boot manager and put something bad in there, or to tamper with the MBR or boot code, BitLocker would be able to detect that and halt the boot process. Basically, it wouldn't let you get at that encrypted content on your other partition that's fully encrypted. So that's a really nice enhancement.
Cool. So let's dig a little bit more into this. Come on, let's BCD. What's that? What's going on here?
Yeah, BCD is one of the everybody's favorite features for the developer base. If there's developers out there, this is the face that you can revile for a little bit if you're having trouble figuring out the right switches to BCD edit. Really, the story with BCD was that we knew EFI was coming, and we had to support it. In fact, EFI started out as EFI, became this thing called UEFI, Unified EFI Forum, and a whole bunch of companies got together and said we got to move off of the 16-bit thing to the EFI platform. So it was sort of this industry thing, and we're trying to do our part to help facilitate that. Absolutely. So we knew EFI was coming, and we knew it wasn't going to happen overnight by any means. There's just no way practical that you've got all these people out there. So what we wanted to do was, since we couldn't flip the switch, we wanted to abstract the firmware that's running on a system from application developers and from end users. They shouldn't have to know that it's a UEFI platform or if it's a BIOS platform. Doesn't really make a whole lot of sense. So we had to come up with a mechanism to abstract any of those differences. One of the big differences is that on the BIOS platform, you've got like that BIOS boot order that's sort of like a proprietary thing that's firmware dependent. It depends if you got like a Phoenix BIOS or Inside BIOS or AMI BIOS or what have you. It's going to be a little bit different how that's managed in their CMOS. Okay. And on an EFI platform, you've got this NVRAM, which is sort of a more standardized thing that allows you to manipulate boot options. And you also got your, everyone's precious boot-ini as well on the BIOS platform. So we didn't have a boot-ini when we did the EFI stuff. We didn't on i64. We just didn't need it. But looking at moving into this into the mainstream, we realized that we had to have some unified thing. So we came up with this idea of having something called boot configuration data, and that's supposed to be firmware independent. And so that stands for BCD, that boot configuration data. And So we build an API for manipulating these things. It's like a nice kind of bit of infrastructure for us. I'm pretty proud of the architecture of that. It's really cool. It supports abstract data types and allows us to not have to kind of deserialize everything into a string format like you see in the boot.ini. You can kind of keep them in like a sort of a smarter format for us. It's easier to deal with, and we don't have to do all of these awful string manipulation, parsing kind of things.
Regex stuff.
Yeah, so
are these, but they're not, I mean, what are they? I mean, they sort of a quasi-binary blob?
Yeah, I mean, you can think of that. It is that. The BCD store is like this proprietary format today. It's really a registry hive, like the other, hives in the system are. But we've got a set of APIs that people can use to get at this. We ship this tool called BCD Edit. We've got some UI in the box to manipulate it, and we've got a WMI provider to allow for scripting. So it's like this request we had from people to be able to manipulate these things in the past, and it was always kind of a pain because people were doing regex and stir and Perl scripts and such to manipulate it, but it was not very much fun. And for that matter, things weren't well documented either. So we built this BCD WMI provider. We've got everything documented up on MSDN. So it makes it, I think, a lot easier for people to understand what they have to manipulate, for people they're trying to deploy. For the most part, end users don't have to manipulate their boot options. They don't even know that boot.ini exists necessarily.
Sure.
If you look in XPSP2, for instance, that file's marked as system, hidden, read-only. So, users don't even see the thing. It's really only maybe developers that have to do this because they need to enable a kernel debugger, or there's some kind of strange things you want to do that aren't totally commonplace. But our developers, of course, have to do that. So we've heard a lot of feedback on that when we built this BCD Edit tool that have tried to take as much into account as possible so we can improve it, and want to do a lot more in the future to provide them a good experience. And it's been interesting to see people pop up with various sort of third-party UI tools for manipulating the BCD options. That's kind of been fun to see people kind of run with this thing a little bit.
Excellent. So just to be clear about this EFI versus BIOS, it's either or, right? I mean, you're going to go the BIOS model or you're not. So, for example, I have a laptop. The name of the company I won't mention because this is not a good thing to do. But I'm having problems with it, so I upgraded their BIOS on Vista, and that did a bunch of weird things. Finally, I have it stabilized now. But so I guess from what I'm really trying to ask you is, it's the OEMs, it's the producers of hardware are the ones that are going to make the decision that I'm going to go EFI or I'm going to go BIOS.
Yeah.
And so why would they choose to go BIOS? Just so they could
compatibility.
Yeah.
So they want their users to be able to. They want to create a platform that supports the last 3 versions of Windows or whatever it is. So what we actually expect is there to be a transition where for a while these platforms will support with both BIOS and EFI. And so that will allow our operating system to start taking advantage of the EFI firmware. And then eventually, when the platform vendor no longer wants to support the OSs that require BIOS, they can get rid of that BIOS portion and we'll just have straight native EFI.
Yeah. So nothing's ever simple. And what was amazing was with this EFI thing, I started out and we were really interested and super focused on doing 32-bit support and getting the 32-bit x86 platform to move over to this thing. Well, it ends up that this x64 thing emerged kind of in the midst of us doing that, and we realized that really in the next few years we hope to see a mainstream transformation of people just en masse kind of moving over to 64-bit computing. I mean, it's kind of the wave of the future. So we set up this UEFI thing, this UEFI forum to really support x64 native boot. That was like our primary motivation. So we did a lot of work to make x64 boot, x64 UEFI boot happen. And in fact, we don't even feel like we need to support 32-bit UEFI boot at this point because that transition's happening. People have got the 64-bit processors by and large for anything new they're buying today. So, so what that means is for these manufacturers, they're going to ship this like hybrid system, and the system is either going to hand off to us running and booting in UEFI 64-bit mode, but if they want to run XPSP2 on that piece of hardware, what have you, it's going to go into this sort of compatibility module that supports BIOS boot, and they'll boot via that thing. So it's kind of kind of an awkward transition for them where they're going to support both of those interfaces, though we'll only have to use the 64-bit ones as we move forward.
So what's the experience been like all these years? I mean, you guys have been in Windows for a while, right? How long have you been in Windows?
I've been in Windows for like 11 or 12 years now, so
wow.
it's crazy to think that I was looking at EFI specs probably in 1999 or something like that, and I got one of the first Itaniums in my office. I got the A0 stepping Itanium, when we did like initial bring up on this thing. I got that booting, so it's just been crazy to see that we finally seen this huge boot manager project kind of coming through to fruition, and see it running on people's systems. It's really exciting. Like we had these plug fests recently for UEFI, and we had like all kinds of partners there. They were booting their x64 platforms out there, and it's interesting because everybody does something like a little bit differently, and EFI is really well specified compared to sort of the organic nature of the BIOS. There was not really a single specification anywhere. But even with that, there's slight variances, and it's just like incredibly gratifying to see all the different vendor systems out there kind of bringing up and going and seeing this big tipping point that's been leading up for a long time and finally seeing it happen. So
that's awesome, man.
Yeah.
How about you, Jamie?
I started here in 2001, so
cool.
I kind of started right when Andrew was thinking that we needed to
write some code.
Move. Exactly. So when we needed to bring EFI to x86.
That's cool. So I mean, like, what got you guys interested at this level? I mean, this is not, this isn't like, some people want to write kernel code. They want to write Win32 code. They want to write, .NET applications.
Yeah.
What got you guys into this low level stuff?
I think we're both kernel guys, and what's fun about this project is that you're basically writing a single threaded kernel. You get to touch all the different subsystems. You have I/O, memory, what have you. You basically you get to work on everything on every part of the platform, and
that's
to
cool.
a lesser degree. So.
Yeah, the thing that just really fires me up about this area is that we're the guys that really get when the pedal meets the pavement. We're the ones that define a lot of the PC platform, right? We're the ones that like help tell the difference between your favorite HP laptop from your Lenovo laptop from Toshiba or whatever. We're the ones that get to like really see those differences and abstract those up to people. So it's like it's a real challenge to come up with the software abstractions that will run across all of those things. It's really, really fun to kind of see your way through all this like specification soup. I mean, we have to support every spec out there. So it's been really fun to work in all those different spec committees and such.
That's awesome. I mean, you just said it. I mean, when you think about how many different hardware platforms Windows has for many years supported, it's pretty amazing. Right, we're not restricted to one type of processor. We're not restricted to one type of configuration, and in fact, we can even run on Power PCs now, right?
Well, we've done.
Macs,
we've had a lot of guys that have run on Power PC things in the past. We don't ship that right now, but we've definitely done. We've supported Power PC and MIPS and Alpha and the x86, and looked at all sorts of other different kinds of architectures as well. So it's really interesting to build this really portable environment. Portability is a really big challenge, but
excellent.
But one that's been really important for this project.
Absolutely. Well, hey, man, it's great to meet you guys. You're pretty much the people of Windows that no one really thinks about, right? You press the computer on, and there's a lot of magic that actually goes on. You might see a few words scroll by, and then the Windows logo pops up. But a lot of stuff has gone on before that.
That's right. Our OS loader runs in like 1 or 2 seconds, but
pretty awesome.
There's a lot of stuff that happens in those.
Well, that's great code, man. Right? It's very performant, very efficient code.
That's right.
Right?
Yeah.
You don't have anybody helping you in kernel world with your memory management and which is a very interesting thing. You mentioned it's a single-threaded world where you get to touch all these different things. But it's really interesting to think about code running without a memory manager. So you're pre-Landy Wang.
That's right.
There's no Landy helping you out.
No.
That's really, really cool.
Yeah.
Well, hey, man, is there anything else we should touch on? I mean, that you don't think we got out there about Vista Boot?
No, I think we hit most of the main points.
That's awesome, man. Well, it's a conversation. It's been great to meet you guys, and fantastic work.
All right, thanks.
Thank you.
All right.